Today, I'm going to talk about aspects of cosmic ray detection in Antarctica. Cosmic rays are composed of atomic nuclei stripped of their electrons. The great majority of cosmic rays we detect on Earth is actually produced in our own Milky Way. Although we don't know what or where the sources are, we know that cosmic rays must be accelerated by powerful shock waves propagating through turbulent magnetized plasma, which can occur, for example, around supernova explosions. After cosmic rays are propagated through magnetized interstellar medium, they eventually hit the top of the Earth atmosphere, collide with air molecule, and initiate a particle cascade. The secondary particles produced, mostly kaons and pions, can interact with the air molecule again, thus continuing on the cascade process, or they can decay into muons and neutrinos. They can be detected at the surface or under the surface of the Earth with ground-based observatories. When particles propagate in denser air, they have a higher chance of new collisions, therefore continuing the cascade process. This happens when the air is colder, for example, during the night or in winter seasons. On the other hand, when particles propagate in thinner air, they have a higher chance of decaying, therefore producing more muons and more neutrinos that can be detected at the surface. This happens when the atmosphere is warmer, for example, during the day or in the summer seasons. The secondary particles produced in cosmic ray cascade processes can be observed in Antarctica by the IceCube Neutrino Observatory, which is actually composed of two detection arrays. One is a surface array called IceCube, which is dedicated to the detection of showers produced in cosmic ray cascade processes. And one is the ionized neutrino array dedicated to the neutrino detection, but that collects most of the event from high energy muons produced also in cascade, cosmic ray cascade processes. Since in Antarctica, we have 1 day and 1 night, the daily variation of the temperature in the atmosphere coincides with the seasonal yearly variation. This can be seen on the top plots, where the temperature corresponding to different atmospheric altitudes that are labeled in their corresponding pressure level in hectopascal show a minimum value in winter, which in Antarctica happens in July, August, and a maximum value in summer, which happens in January, February. On the bottom plot, you can see that the daily rate of high energy muons as measured by IceCube follows very close the mean temperature corresponding to the atmospheric altitudes where most of the muons are produced. Not only you can see the seasonal variation is very well reproduced, but also all the variations at smaller time scales. Well, we can take exactly the same muon events and reconstruct their arrival direction distribution. We know that the muons, high energy muons reaching the neutrino observatory in IceCube are within a fractional degree from the primary cosmic ray direction. Therefore, if we make a map of the arrival direction of the muons, that actually is the map of the cosmic ray arrival direction distribution. We can actually compile a map in relative intensity that highlights where in the sky a cosmic ray flux is higher than the average over all the sky, or is lower. We can actually therefore see that an anisotropy exists of the cosmic rays, and the amplitude of anisotropy is very small, is of the order of 10 to the minus 3. Since IceCube collects 60 billion events every year, we can actually measure this small amplitude with very high statistical accuracy. We can actually do better than that. We can combine the observation from IceCube, which is 1/3 of the entire sky, with observations from other experiments located in the Northern Hemisphere. In this case, we combine IceCube data with those collected by the Hawk Gamma Ray Observatory, which is located in Mexico and 90 degrees north. With all the two experiments data combined, we can have a complete view of the cosmic ray arrival direction distribution. We can analyze the sky by decomposing it in spherical harmonics, which allows, first of all, to filter out the large-scale feature and visualize the smaller scale feature, which are very likely related to magnetic field structures in our local interstellar medium. but we can also make a graph of the power spectrum for the different angular scales, show that the large angular scales are more powerful than the small one. And this information can give us hints on the underlying processes that produce the anisotropy. Thank you very much.